Good morning, everyone. Today we are going to talk about the final project for the class ME 522 Mechanical System Design. Our final project title was Shimano Shiano 1000 FE Fishing Reel. And my team members are Andrea Savalas, Christian Guzman, and myself, Rajesh Kumar Murugesan. Now I'm going to talk about the outline of today's presentation, starting with product description, project goals, project challenges, solid model images and unique commands that we used, file management and sub-assemblies, kinematics, rendering, and finally we're going to talk about the comparison of models. In the next slide, Christian is going to talk about the product description.
Some discussion about our fishing reel is used in freshwater. The manufacturer is Shimano. While the assembly, we counted 57 parts, and from all of them, 53 are unique parts. And the material used is the polypropylene and stainless steel, as well as aluminum. Now, Andrea is going to talk a little bit about the project goal.
As part of our project goals, we have the creation of an accurate CATIA part modeling, a generation of precise CATIA part drawings according to the guidelines, a creation of a true CATIA assembly and its drawings, and a creation of effective kinematics in motion and a detailed rendering. Now, Rajesh is going to talk about the project challenges.
While designing the fishing reel, we experienced some challenges, and we split the challenges into minor difficulties and major difficulties. The minor difficulties are poor design accuracy. As we mentioned before, it has multiple parts, and also it's more complex in shape and very smaller in size, so it becomes more complex for us to getting the exact dimension and also designing to the exact complexity of the different curves over there, and also the presence of gear. It involves the gear tooth and designing the gear tooth exactly the way it will matches with the next other gear. It's a difficulty for us, and we overcome those difficulties. And the next one is the file management. As we mentioned, it has 57 parts, so we need to we are in the need to manage our files properly. So we just implemented sub-assemblies to avoid any difficulties. And the major difficulties are kinematics and assembly management. Since it has multiple parts, we used multiple constraints to assemble properly to that entire assembly, so that we will avoid any conflict in the end. Up next, Andrea is going to talk about the parts that she designed.
Well, in this slide, you can see the model images of the parts that I have designed. These parts were modeled using different workbenches, such as part design and generative shape design. Next, you can see the pictures of my three complex parts. So the first one I'm going to talk about is the body that you can see in the number 13. So basically, when modeling the body, as it contains many functional parts, it was very important to first assemble all the internal parts and then start creating. So this will assure it will be a perfect fit with all the internal parts. Next, I want to talk about the drag knob that you can see in the number 14. So this part contains a thread and a gear in one side and an ergonomic shape in the other side. So the most challenging part of modeling this part was the creation of the X shape in the knob. So this was important to maintain the ergonomic shape, and for solving this problem, it was required to use the appropriate pocket up to surface. Finally, I want to talk about the bail hold support, as you can see in the number 15. So this part should be modeled within the assembly. So this allows to pull out all the dimension of other parts. So as this is an embed part, the optimal way of doing it is like using the projection. One tool that I use and we never touched in class was the boundary. And basically this command allows us to propagate any select edge around a surface boundary. Next, Christian is going to talk about his parts.
As you can see in this slide, I present the part that I designed. For most of them, I use part design workbench. I use a features from the generally shape design in order to complete the model. In this slide, I present the 3 more complex parts that I designed. For all of them, I use surfaces designs, as you can see. And the picture from the left is the bale cover that starting from a sketch, going to a multi-section surfaces using several different splines, and finally making a closed surface in order to give a volume to the part. In the picture from the right is the rear surface, rear cover. It's starting from the extract surfaces of some other parts, and then uses multi-section surfaces and going through trim tools. I generate the complete surfaces of the rear cover, and then also giving closed surfaces in order to give a volume to the part. Finally, the rotor, which is the picture of the bottom, I use several different tools, which is the multi-section surfaces and the pocket, using as surfaces and a direction specified by the user. This allowed me in order to complete the model of the rotor. Finally, one tool that I use and I found really important is the extrapolated tool that allowed me to expand one surface in the direction and the boundaries specified of that specific surface. Now, Rajesh is going to talk about a little bit about his parts.
In the slides, the parts shown over there are some of the parts that I designed. All the parts that is in the slide I mostly use part design, and the complexity that I can say in this parts are only the gear tools, since it's gonna match exactly with the other gears. So I'm in the state of designing it exactly precise gear ratio to make sure there is no conflict in gear matching. In this slide, I'm just showing you the complex parts that I designed. And the one in the top left, number 42, is the side cover. Since it involves multiple cross-section, multiple multi-section, and also complex shapes, it takes more time for designing. And also I used generative shape design and part design to complete this design. This part is going to fix exactly with the body part, so the outer dimension need to be precisely designed exactly to the other part to avoid any conflicts. It involves different complex shapes, so I just used trim and trim by piece command to get those complex shapes. The next one on the right side is the number 43. It's bale spring cover. It's gonna cover the bale spring and the 3 different parts in the rotor assembly, and also it need to be designed exactly to avoid any conflict of keeping the parts inside. Also it's gonna stay over a groove in the rotor, so I just designed this part in the assembly workbench by taking the outer curves of the groove for this external sketches to get the desired shape. Here I just used 2 different workbench. One is part design workbench and surface and shape design workbench. In this I just use one tab using part design, one tab using surface design to just check how exactly those 2 will differ. And up next in the bottom is the handle assembly. In this, the handle arm is the one having like different dimension, like different cross-sectional area along the length, and I just used different multi-section to get this desired shape. And the unique command I used in this project is the enhance scenes I used during the assembly workbench. It helps you to create the exploded view of an assembly without disturbing any constraints or any position to the actual assembly, since it will save the files in the form of application. As you seen in the image, it's just creating an scenes in the application, so it will be easier for you to create an exploded view drawings. You just need to select the scenes to get the exploded view drawing. Up next, Andrea is going to talk about the file management.
As mentioned before, the fishing reel has 57 parts, so file management was the key for a precise assembling. So we decided to divide it into 5 different sub-assemblies, as you can see in the tree. The first one was mentioned before by Rajesh and corresponds to the handle. The second one, it's in the picture number 1, corresponds to the body. The second one, the spool. The third one, the roller. And finally, the handle cap. This helps us to properly constrain all the parts and make all the necessary changes like really easy. And then finally create a true CATIA assembly model as one of our project goals was. Next, Rajesh is going to talk about the final assembly view.
The image shown in this current slide are the final assembly that we got after giving proper constraints and pulling out all the parts that we designed. That one on the left is the isometric view of the assembly that we designed, and also the one on the right is the right side view of the design. The next is the kinematics. We just experienced a little bit of problems in kinematics because of the presence of helical worm gear. So we tried all possible way to run the kinematics, but we can't able to run it. But we did the kinematics for the handle assembly to spin the handle on the body part. This is the actual video of the kinematics that we did. Up next, Christian is going to talk about the detailed rendering.
As one additional task that we did for our project is the render task. We wanted to see how it's gonna look like our final product in one particular picture, as you can see now in the boat. Finally, what we did is comparing our product from the assembly with our final product that we already had. As you can see, the picture of the LED is a rendered product from the assembly, and the picture from the right is the product that we acquired from the beginning. Thank you very much for watching.